Hi everybody, this is Professor Iris Miano. This is a day are we on? 14 lecture. Let's see. Yeah, day 14 lecture video on measures of center and measures of spread. So we're going to cover two sections in today's video. And the first thing that we want to do is give a general idea of what measures of center are. So there's going to be several different ones that we cover, and different ones are going to be appropriate for different data sets. But generally a measure of center is meant to capture a typical value. It doesn't always capture a typical value depending on how the data is spread out or what the values are. Anyway, it is meant to represent a typical value. Now let's get into some notation here, and we're going to talk about the population mean versus the sample mean. So there's some formulas that we want to encounter here, and so let's go ahead and make sure that we write those down. Yes, using the population and sample bits of notation. So hold on just a moment. I'm just checking my notes here. I want to make sure I get all the notation here. So the population mean is represented by the Greek letter mu, and it is the sum of all of the data points divided by, oh, excuse me, let's actually get rid of that last line. It's not quite in the right position. Just a moment. Oops. Okay, so you sum up all of the data points and then you divide it by the entire population, right? But if you're talking about a sample mean, well, the notation is a little bit different. You use this X bar, or yeah, X bar is the way that we'll describe this. X bar. That in quotes, because that's the way you're supposed to identify this verbally, and that'll be the summation of all of the data points divided by the sample number. Okay, so defining some of these elements here, we've already defined to a certain extent the summation, the sigma. So this is a sigma, and it's a summation notation. X sub I is a data point. Inside of the summation notation, it's meant to be the sum of all of the data points. And then lowercase n is the sample size. So the number of data points in the sample, whereas capital N is the size of the entire population. Now, depending on how large the population is that you're trying to conduct the study, a certain study on, it might be too large for you to take data from every single individual in the population. So this is why we rely heavily on calculating things for the sample, and the sample mean is so important for statistical studies. You just have to take a small portion, a relatively small portion of the entire population whenever you're trying to answer a question about that population. Well, oftentimes you'll have to do that. So that's where statistics really shines, okay? Great. Let's go ahead and define our first, or our second rather. The mean is going to be, let me define this a little bit further. I just wrote down these formulas but didn't actually tell you what they mean. So the mean, or the average, that's another way to describe this, or average, is calculated from a data set when you add up all of the values in the data set and you divide by the number of values that you have. So for instance, if you have a data set of the heights of 10 people and you want to find the mean height or the average height, you would add up all of those heights and divide by 10 in that scenario. All right, so that's our first measure of center that we're defining here is the mean. There's also median, and we're going to talk about what's the other one called? We're going to define mode. It's actually not a measure of center. Another measure of center that we're going to talk about is mid-range. So something to look forward to there. The next one is median, and this is the middle value of ranked data denoted by capital M. Okay, so I'll just put parenthetically capital M. Okay, and to find the median, there is a two-step process here. You want to number the, order the observations from smallest to largest, or data. You could call them observations or data, from smallest to largest. To just a moment, largest. And then if it's if you had an odd number, if n is odd, then find the centermost value. So the exact middle value in the collection of ordered data. But if n is an even number, then you have to find the average of the two middle observation. Take the average or mean of the two centermost, or center, we'll just say center, values, which would be adding them both together and dividing by 2, because both means 2 of them. Okay, cool. Now let's go ahead and find the median of the given sets of values. So the first thing that you'll want to do is order your data. So ordering, we'll get the smallest value is, it looks like 20. And then we have 2 values of 23. And these are observations. This is data, so it's not like in other set situations in which we were instructed to not display repeats. You definitely want to display repeats here. We have a special word associated with the most amount of repeats. That's the mode coming up here. So 20, 23, 23, 30, and then 52. So notice that I've reordered the data from smallest to largest, and since there are 1, 2, 3, 4, 5 values, that's an odd number, I'll go for the exact center value, and that gives me my median. So in this case, the median is 23. Capital M equals 23 is appropriate notation there. Now for number 2, ordering them from smallest to largest, we will have the smallest value appears to again be 20, then there's 2 23s, a 24, a 30, and a 52. So it's basically the same data set, except for there's an extra value of 24 stuck in there, and that makes the entire number of data values an even number. There's 6 of them, right? So here you have to take the average. Oops. Actually, I want to change the color here. And so that'll be 23 plus 24 divided by 2, which equals what? 23.5 equals M. in this data set. All right, go ahead and box those up. Great. All right, so now you know what to do in order to find the median. Now, you know how we're talking about repeat values? Well, in your data set, if you have repeated values, the mode is going to be the value that gets repeated in the data set the most. So by definition, it's the data point that occurs most frequently. Some things to note here that we want to make sure that we understand that a data set may not necessarily have a mode, and that'll be if every single data point is distinct. So yes. Furthermore, there can be more than one mode. Oops, let me go ahead and try that again. There can be more than one mode. So let's say you had a data set and it happened to have two repeated values, and they both repeated 2 times. Well, since it's an equal number of repeats for the repeated values, then both of those values that are repeated would be the mode, provided that there wasn't any other value that was repeated more times than that, then that would be the mode. But there can also be no mode. There can be no mode if each observation is distinct. Okay, so let's find the modes for a few examples here. Notice that 23 occurs twice in this data set that looks very familiar from the previous example. And then all the other data points are distinct, so that means 23 is the mode for that one. For number 2, notice that each data point is distinct, so this one has no mode. And then here, for number 3, we have 23 occurring twice and 30 occurring twice. And then otherwise, the rest of the data sets or the data values are distinct. So we have 2 modes, 23 and 30. Cool. Mid-range. All right, so the mid-range is the value between the largest, value midway between the largest and smallest values in the data set. Okay. So you have to know what your largest and smallest values are, and then take the average of them. So find largest and smallest value. Values. Let them be L and S respectively, if you like, just so that we could come up with a formula for this, and then take the average. Just a sec. Take the average. Of L and S. Okay, so the mid-range equals L plus S, largest and smallest values, divided by 2. Cool. And that's all there is to that. Moving on. Effect of extreme values. Okay, so depending on what kind of distribution you have in your data, excuse me, hold on a second. You can have outliers making a big difference in your data or in your measures of center, depending on which measure of center you are choosing to represent your data. So the mean is sensitive to outliers. And you may be wondering, well, what's an outlier? It's an extreme value, either extremely large or extremely small, compared to the rest of the data. Well, the median is not sensitive to outliers. And you may be wondering why. Well, the mean is calculated based on the actual values that are given in your data set. So since based on values of data, so really large values and really large or small values are going to have its effect on where the mean lies, whereas the median is not selected by virtue of the values of the data. It is simply the middlemost data point, so there's no pull that's going to be occurring one way or the other by any extreme values. It's still going to just be the centralmost value when you order the data from smallest to largest, since not based on values of data. Okay, so let's talk distributions and skewness for a moment, okay? And how the mean and the median can compare to one another depending on what your distribution looks like, okay? So the idea here is to say that unless the data is uniform, the mean and median can be compared. And by saying can be compared, I'm saying that they're not going to be equal to each other. Because if you have a truly uniform distribution for your data, then the median and the mean are going to be equal to each other. And even if it's not truly uniform, if it's like pretty uniform, you can still see that the median and mean are going to be very close in value, okay? So let's go ahead and draw some distributions here. Let's start with a this is a uniform distribution. Just looks like a bell. And a skewed left distribution would look something, oh goodness gracious, I'm already making it look silly. Gonna have a tail on the left and its hump over here, whereas a right skewed distribution would have its hump early on and then a long tail over on the right. Okay, so this is, again, sorry, left skewed and right skewed. Okay, so what do we want to say about this? Here, let's go back to the uniform, and I'll put a different color on here. Let's go this bright green color, and we'll say here the mean and the median are about the same. Mean is equal to median, or are very close in value. Whereas in a left skewed situation, the mean will be less than the median. So I'll say mean is less than median. Okay, so the mean is going to be pulled to the left because there's more values in these extreme areas right here. The lower values, I guess, are going to have their pull. So let's say maybe the mean is here, but the median is somewhere over here, right? Median. Whereas with the right skewed, you're going to have the opposite scenario here, where the median is going to be less than the mean. Or you can say, if you want to do the same comparison, the mean will be greater than the median. Okay, so let's say that the mean is going to be pulled to the right compared to the median. Let's say this is the median, and then this was the mean. All right, yeah, there's going to be some effect by the fact that there's some values that are quite large compared to the more typical values. They're going to have their pull on the mean that is calculated based on the actual values of the data, whereas the median is just the centralmost value. Okay, cool. So hopefully that is landing pretty well. Okay, so now is the time where we're going to take out our calculators and fiddle around with them a little bit. So this is going to be kind of challenging for me to do in this video because the only thing you're going to be able to see is my screen. So I'm going to, in the process of going over this example with you, I'm going to write down the series of keystrokes that I take on my TI-84 Plus calculator. Now if you have a TI-83 Plus, your buttons might be in slightly different positions, but you're still going to be pressing the same buttons. And if you don't have any TI-84 or TI-83 calculator to work with here, then you're not going to be able to follow along with this example. Okay, and you're going to want to the best of your ability, figure out if you can procure a TI-84 Plus or TI-83 Plus calculator. And this has already been noted in your syllabus. This is something that I've mentioned like even before class started, that this was a necessary piece of machinery. I'm not sure if the SMC Math Lab is still renting out calculators, but if they are, you'll want to set up a time where you can go pick one up or have it mailed to you. That's definitely something at least one person in class has had that set up for them. So it's your responsibility. I mean, I've done a couple of events in class where I've had you guys tell me that you need calculators still. Hold on just a moment. Oh, sorry for the interruption there. Anyway, where were we? Calculator. You want to get your hands on a TI-84 Plus or a TI-83 Plus in order to do the statistical testing that we need to do for this class, okay? It's not much that we're going to learn about using our calculator, but it's vital for your preparation in the introductory level statistics class that we teach at SMC. That's Math 54. Okay, that being said, what you'll want to do is go to Mode. So the first thing you want to do is make sure that your calculator's in the right mode. So let me put this in a color that's a little bit more good, more better. Anyway, calculator steps. You want to go to Mode. It's a button. And then from there, so it's probably on like close to the top of the collection of buttons that you have on your calculator, and you want to scroll down to the second page. Then scroll down to second page of options. There's a lot of options here. Until you find, it's called Stat Wizard. and it's going to say on or off. And so you want to just make sure that it is off. Okay? Then you'll quit out of that. So second quit, then second quit, which is also your mode button if you have a TI-84 Plus. Second mode, which is quit. It should say quit on top. Okay, and then you're going to press the stat button. Okay, stat. Okay, and then you can press enter or go to number 1, which is edit. 1:edit. And also it'll have a ... after it. Okay, and then that's going to take you to your table where you're going to put your values. So your table should have column headers of L1 and L2. So you'll look at something that looks like this. L1, L2, L3, and then you can have more if you want to. And there'll be a little like cursor right here where you can start putting in your data. If you're and you want to put your data into L1. Now what's the data? That's this business right here. Okay, these are the values that you want to put in one at a time. So if you already have data in your L1, just go ahead and highlight L1 and then press clear and then move down. And you'll clear that entire column of the old data because you want it to be empty. And then you want to enter in the data points, which are 5 and move down, and then 8, move down, 5, move down, 4, move down, 6, move down, 5, 7, 8. Now that's the first row of data. Now go to the next row and put in 9, but stay in L1. Okay, you're still in the L1 column. 9, 12, 5, 5, 7, 5, 6. And you should have 15 data points altogether. Okay, so from there, you don't have to quit or anything like that. You're just going to enter your data. So enter data. So that's this stuff that I'm pointing at here. And then you want to press stat again. And then move over from the edit column over to calc. So move to calc, which is a heading, and from there you want to go for the first thing written, which is one variable statistics, var stats, and you press enter there. Okay, and then you'll see on your home screen at that point it'll say one variable stats and a little cursor, right, blinking. And here the blinking thing is just where you would put the name of the column that you put the data in, but lucky for us, we put our data in L1, the very first column in the edit screen, right? So if you just simply press enter at this time, so press enter, you're going to get the data that you seek. And so it'll look like this. In black, it'll be a black box on top and it'll say one variable stats. And then you'll have what? X bar equaling some number, and the next one will be the summation of X. equaling some number, and the summation of x squared, which, like, why would you need that? I can't even tell you when you would need that. What else? There's S sub x, which is actually the standard deviation. That's something we're going to talk about in the next section for spread. And then there's sigma x, which is the, population standard deviation. We'll talk about that as well. And then you can pull the down arrow, push the down arrow in order to see other page. And then you'll get n, right, equals some number. That's going to be your population size. What else are you given? Min x, the minimum value, some number, Q1, which is the first quartile. Again, talk about that at a later time. That comes up in the box plots section, 4.3, Q1, oh, actually they don't give you Q2. They give you the median, which is the same as the second quartile value. You're like, I don't know what you're talking about. Don't worry, this is a topic for another time. Median is next, and then Q3, right? And then the very last thing that they'll give you is the max x. Okay, so those are all of the values. You got to scroll down to see them all from the one variable statistics. So this is something that we're going to be using again and again with data sets, and especially when the data sets are quite large, it'll be very advantageous to us to have this information at our disposal without having to calculate it by hand. So the mean, according to what I put into my calculator here, what I was able to calculate was, let's see, 6.46 is forever. So let me go ahead and report that. The mean is the x bar. So that was the very first, the top thing that was presented in my one variable stats output. And so it'll be 6.46, and I'll put a vinculum on top of that 6 because it repeats forever. And then the median, I'll scroll down to the third to the last thing in that report. The median, m, equals 6. And going down below, the mode. Now the mode is not something that this variable, one variable stats, has an output for. So we have to just look at the data and see what value, if any, occurs most often. So notice that there are 1, 2, 3, 4, 5 different data values that are of, value 5. And although there's some other repeats, none of the other repeats repeat as many times as the 5. So it looks like the mode is the 5 here. Mode is 5. And the mid-range. Now the mid-range is not something calculated here in this one variable stats either, but the elements that you need to calculate the mid-range are there, because it'll be the max x minus the min x over 2, which is what for this one? Well, the min x is 4. Oh, excuse me, I want the max first. My bad. We'll go. Max is 12 minus the min I already said was 4, and we divide that by 2. So that'll be 8 over 2, which equals the 4. Cool. And I'll go ahead and change the color to something real bright so I can box up all of my answers. Great. So as you can see, the mean is pretty close to the median, but in the mode, I mean, whatever, that's not really a measure of center, it's just the most often, I mean, I guess it's a measure of center because it's like if that data point happens a lot, then it's going to have a pretty good influence over your mean and yeah, and things like that. But it's less reliable as a representative value of the data. And then the mid-range here is just kind of like wildly off because it's the same value as the minimum value. So yeah, not all measures of center are created equal. Depending on your data set, one or another could be a better representative, and it's just all about experience, having experience with the stuff, and being able to make that judgment call. Okay, so that's it for this first section on measures of center, and now let's go ahead and dive right into measures of spread. So the range, how do we want to define this, is given by, it's basically the difference between the smallest and the largest values. What color are we on? Oh, we need to add notes here. And let's choose this royal blue color, why not? The difference between the minimum and maximum values. Okay. Cool. Let's talk about variance. Now, variance doesn't really come up a lot in our endeavors, but it's definitely something that needs to be defined so that you're ready for it when you see it in your next level class, your Math54 introductory statistics. We are more concerned with standard deviation, which is an offset, or an offshoot rather, of variance. But so in order to understand standard deviation, we first need to understand variance. Okay, so variance is described as the sum. Oh, and sorry, variance is V. Let's start with the sample variance, actually. V is going to be basically S squared, which is the sum of the differences between each observation, so that's x sub I, and the sample mean, all over 1 less than the sample population size. Whereas, oh gosh, hold on, I'm getting a phone call. Just a second, guys. Okay, thank you for your patience on that. I know it's not even like a second as far as you're concerned with this video, but I appreciate you having patience with the pauses that I have to take sometimes in recording these. Okay, so really there's no V to this. It's really just considered to be S squared, which is interesting that the variance is intimately acquainted with what the idea of the standard deviation is, which is what we'll get to in a second. So the population variance, on the other hand, uses a Greek letter called, let's see, but it's squared. And that'll be the sum of the observations subtracted off the population mean. Okay, which is mu, and then have that over 1 less than the entire population value. Okay, so, oh, and I'm so sorry, these are squared, right? Yes, I forgot to put little squares here and there. Okay, but, you know, population variance or population standard deviation, population mean, this is not a thing that is generally able to be calculated. So what we really want to be focusing on here is getting to know these sample elements: variance, standard deviation, and mean. Those are far more relevant to our purposes here. Okay, where x sub I minus x bar is the that's the distance away from the mean for every data point. So the data's distance from the mean. So it's basically a measure of how far spread out the data is from the mean, which is one of several different kinds of measures of center. And then this is the data's distance from the mean squared. Sorry, let's clean up the handwriting a little bit there. Squared. We don't really need to put too much into understanding how this is derived. We just want to be able to understand the notation and use it. So it's just like the focus here should be understand the notation and use it. Be able to use it. And furthermore, the standard deviation is defined as the square root of the variance. So hopefully that is something that we will enjoy, not having to like learn an entirely different formula here. So I'll say SD for short is the square root of the variance. And you may be wondering, well, why do we care about any of this stuff? Well, these values, particularly the standard deviation, is going to give us an idea of how spread out the data is. Because if the data is really spread out, it's not going to give us a very good indication that the measure of center is very representative of the data. Whereas if it has less spread, then we can be certain that the measures of center that we choose to use are good representations of the data. So population standard deviation is the square root of the population variance, and the sample standard deviation is the square root of the sample variance. Here we go. So that'll be just S equals the square root of, oops, that's not what I wanted. Don't want an E, I want a summation. Simple, which looks like this. Xi minus x bar squared all over n minus 1. Okay, whereas sigma equals the square root of, oops, that is not a very good summation symbol. That looked like a 5. Let's try that again. Better. Okay, xi minus mu, which, if you recall, is the population mean over n minus 1. And capital N is the population size. Cool. So yeah, great. So the standard deviation is our general measure of spread. Okay, so some things to note about relative sizes of standard deviation. If the standard deviation is small in value, then that means the data has less spread. I kind of alluded to this already. Making the measure of center that we choose a more typical value. Whereas if it's the standard deviation is large, the data is more spread out. Making the measure of center less typical. Okay, what's next? Okay, here we go. Now, this next example is ages of 5 students in class. Okay, so we're clearly in some sort of at least community college situation if we're talking about students in a class, because their ages are 23, 52, 30, 23, and 20. Finding the range and the variance and standard deviation. These are things, even though the data set is small, we should leave it to the calculator to calculate. So again, I'm going to describe, but not write down again the series of steps that it takes. You'll go to Stat is the first button you'll click, and then you'll have the drop-down menus of Edit, Calc, and Tests. You want to go to Edit number 1, which says Edit, ... Press Enter. Now, you're going to have data in the L1 column. I recommend that you toggle up to highlight L1 and then press the Clear button and then toggle back down, and you will see L1 column completely clear of the data. Okay, that's how you can do it all in one fell swoop, because we had 15 data points entered in column L1. And you don't want to necessarily clear them one at a time by deleting, delete, 15 times. Like, what a waste of your time. So just go up, highlight L1, press the Clear button, and then toggle back down again. So the data I'm going to enter is 23, and then push it down, 52, down, 30, down, 23, down, and 20. So that's 5 data points altogether. Now press Stat. Toggle over from Edit to Calc, so press the movement to the right button one time to go to Calc drop-down menu, and the first one there, number 1, one variable stats. Press Enter. Press Enter again with you have the blinking cursor next to one variable stats. That's where you want to be. Press Enter, and then you will have all of this information given to you. And within it, you will be able to calculate the range. Now, they don't give you the range value, but they give you enough information in order to calculate it. Because remember, the range is the max minus the min value, which in this case, the max is 52, and the minimum value was 20. So what's their difference? That'll be 32. Is the mid-range, or the range rather. All right. Oops, that's not the color we were using when we were doing this snake loop. Okay, our broil loop. Now find the variance and the standard deviation. That's where we're going to want to go back up to the first page of the one variable stats output. And so the variance is going to be, so that's something you will calculate here. First, start with the standard deviation. So do this one first and this one second, because they don't actually give you the variance. They give you the standard deviation, which is your S sub x in the list of one variable stats. That's the output, and mine is 13.04990. 421, and that's where the decimal ends. So I assume it continues on without any pattern. Okay, so what we are to do with this is to round it to a reasonable number, maybe to the nearest hundredth. There's nothing in the instructions to indicate that we were given any specific value to round to, but I'm just going to make that up and say, okay, the hundredth seems good. So that'll be 13.05. Okay, Now take this number, or as much of the number as you possibly can, and then square it. So what I'm going to do now is second quit, and I'm going to take 13.04990421. Yes, I'm going to take as much of the decimal expansion as I possibly can, and then I'm going to raise it to the second power. Because squaring your standard deviation gives you your variance, okay? So the standard deviation is this number, and then therefore the variance, which is s squared. I keep putting v down, but that's not appropriate notation. The variance is s squared, which is about 170.2, and then nines forever. 9, right? So rounding this to the nearest hundredth, you'll get 170.30. And I know what you're thinking. Is it okay if we put 170.3? I don't have any problem with that. If in the homework you are asked specifically to round to a particular decimal place, and even if it's a zero, you should put that decimal place down. So I'm just working from the assumption that, hey, maybe the instructions dictated that I should round to the nearest hundredth. Well, this is how I would do that, and I guess I'm going to try and be consistent with my pink arrows for indicating the rounding. But okay, there we go. So there you have it. My calculator calculated that for me, and that's all well and good. I have all this extra space here. My colleague, Professor Louis Martinez, came up with this lecture notes here, so I kind of wonder if she went through the time of actually calculating it by hand. Oh, what an endeavor that would be. Let's just go ahead and rely on our machines and do that. Certainly this can be calculated by hand, and just as a reminder, this, right, this s and this s squared would be the way that you would do that. So you'd have to find the distances between every data point and the sample mean, sum it all up, and then divide it by one less than the population size, or the sample size rather. And wow. Or you can press some buttons, right, in a particular order, and the values can be popped out for you. So why not just take advantage of technology there? Okay, but moving on. Let's talk about the empirical rule. So this is where standard deviations really shine as far as being able to give us concrete mechanisms for how the data is spread out. So if you have a bell-shaped curve or a normal distribution, you can assume that approximately 68% of the data lies within one standard deviation of the mean on either side of it. Deviation. So in the area under the curve, that's one standard deviation above and one standard deviation below the mean. That area, it represents 68% of the data. I'm going to outline all of this in the figure down below. So let's just go ahead and finish outlining these proportions of the data in regard to standard deviation length. So if you're trying to capture 95% of the data, so like the overwhelming majority for sure, it lies within two standard deviations of the mean. Two standard deviations above and two standard deviations below. Now, if you want to get even more of the data, you're going to go within 3 standard deviations of the mean. And by then, you can't really go too much further away from the mean and expect to see any more of the data. Okay. Cool. So let's have a quick visual here. Right here where this tick mark is, that's going to be the mean. And then 68% of the data. So let's say we have one standard deviation distance here and here. Here's 2 standard deviations, and here's 3, something like that. Like the standard deviation value is constant for a particular. So I tried to make these equidistant, but this length is a little bit more than that one, which is a little bit more than that one. So just bear with me. Just pretend these tick marks are all equidistant from one another. Okay, so from here to here, right, this area represents 68% of the data. Now I'll change the colors here. Let's go green with it. If we're going here to here with this, what's done in green here, that'll be 95% of the data. And then if I want to go out 3 standard deviations on both sides, let's say that looks like this teal stuff. Well, that'll be all this bit, right? And as you can see, yeah, sure, that is pretty much all the data right there is this teal. That's 99.7% of the data. Cool. So, oh, sorry, let me go back to this and say this is 1 standard deviation is this distance from here to here. So that's supposed to be the same distance from the mean to this other tick mark, and so on and so forth. Okay. Now, here's an example, and we already have a bell curve to work with as far as making a figure associated with the scenario. Suppose that exam 1 had a mean of 72 and a standard deviation of 8. Assume the distribution of scores is bell-shaped. Apply the empirical rule. So right away, we can use this to label this right here. There's 72 right there, and that's the mean. And then if we go 1 standard deviation, 2 standard deviations, 3 standard deviations, 1, 2, 3. So that means that the distance here is 8. So this tick mark right here, the position of the first standard deviation must be, what, 80? Because 72 plus 8 is 80, and this one will be 88, right? 8 more after that. All of these distances are 8, 8, 8, 8, all the way across. And then 8 more would be, what, 96, if I'm not mistaken. And then what's 8 less than 72? Well, that would be 64. And then 8 less than that would be 56. Yeah, and then 8 less than that would be 48. So yeah, and then you can color code this biz where it's like, here's where 68% scored here with data. Let's pick another color. It's really distinct. From here to here. This is 95% of the data. And lastly, what's a good contrast color? Let's go this. Well, yellow's maybe too close to this green, so maybe we'll go this bright orange. And then here, all this, all the red stuff, or the reddish orange, is going to be 99.7% of data. Oh, I should write the words of data in this pink. Great. So hopefully we have a better understanding of what this empirical rule is trying to say in regard to uniform distributions. All right, here's another example. Below is a density histogram of all ages in years of people who attended a movie. Now, notice that the distribution appears to be very uniform. Like painfully uniform. Look at how there's this symmetry here, right? So let's go ahead and use this to estimate M, which is the median. And since it's uniform, the median and the sample mean are, assumed to be either very close in value or the same value. And if we're just estimating here, I would say that both M and X bar are the good estimates for them would be 64, okay? And I'll say that they're same since distribution is uniform. Estimate S. Well, it looks like we can, if we add up the densities of these 4 middle bars here, you get 20 plus 20 is 40 plus 14 is 54 plus another 14 is 68. So check this out. Here appears to be 68% of the data, right? Like that was just worked out so beautifully. I'll make it dark orange, 68% of that data. So that means that this distance from the mean, which was 64, mean is 64, that distance from here to here should be the standard deviation, right? Let's make that even more distinct color. So from here to here is the SD. So what's the difference between 64 and 68? Well, that'll be 4. So I'll estimate that the S value is 4. And S squared, well, just square it. That'll be 16. And that's the variance. Okay? Cool, 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 cool. Let's talk about unusual observations before we wrap up this video. An unusual observation is one that occurs more than 2 standard deviations away from the mean. If you're more than 2 standard deviations away, then you're considered to be weird as far as the data is concerned. Or, you know, weird is just my way of saying unusual. But yeah. So let me go ahead and get a better color going on, which is this dark purple. An observation is unusual if it is located more than 2 standard deviations away from the mean. Okay, so let's entertain this last example in the midst of this definition here. It states, a restaurant states that the average cost of dinner for 2 is $60. So this is your, you know, X bar with a standard deviation of $12. Is a $90 dinner for 2 unusual? Well, let's see. Is $90 more than the mean plus 2 standard deviations? This is what we're asking ourselves. Because if it is, if this is true, a statement right here, then we will say that the $90 dinner is unusual. If not, then we'll say it's not unusual. Okay? So here we go. 60 plus 24, which is 84. Yep. $90 is greater than $84, which is a distance of 2 standard deviations away from 60 in the you know, in the larger sense, right? Well, since 90 is bigger than 60, we only want to test on one side, right? We don't care about if it's how it compares to 2 standard deviations away in the you know, less pricey direction, right? So we'll say yes. A $90 dinner for 2 is unusual. Unusual. Cool. And that's it for this video. I will also have ready for you very soon another video on the next section, just one section, section 4.3 concerning box plots. So stay tuned for that. Thank you all so much for your attention.